So we're in your chemistry book in chapter 7, session 3, quantum numbers and electron configuration. And so we're going to talk about these quantum numbers, and you're wondering, what's this whole chapter about? Well, it's about light, and light comes in photons, and photons are made of energy packets that go right back to electrons. And the electrons are part of the atom, an important part. So as we talked in the last chapter, we talked about Schrodinger's equations, trying to figure out these electron configurations, and he did it mathematically into probability contours around the region, and they take the contour that contains 90% of the dots to see what kind of shape, these electrons as they rotate around the nucleus of the atom are. And they found that they weren't just circular, but they were three-dimensional, and they had certain shapes. So some of these shapes are in your book here, as we see. There's an electron cloud here. This electron cloud shows the probability contour being a circular motion. And then we have electron cloud here, and it looks like, actually they're considered two dumbbells, but it looks like a cross, doesn't it? So here's the electron cloud, and here's the probability contour of that electron cloud. And this is the nucleus in the middle. So very unusual, not what we thought in the first pictures of the atom and Bohr's model. Now we have a new way to put together how electrons are circling or gathering around the nucleus. And this is so important because electrons are important, especially important with light. So let's go into these quantum numbers. We studied about quantum numbers, and quantum meaning packets. These are the packets, quantum numbers. So Schrodinger gives 4 different quantum numbers, and these numbers describe 4 things, of course. First of all, the electron's shell or energy level, the shape of its orbital, whether it's shaped like a sphere like that one, or like a dumbbell, or like a clover leaf. And then the orientation in space. Is it going vertically, or is it going horizontally or diagonally? And onto its spin. Do you know these electrons spin? Or they look like they're turning or spinning one way, positive and negative. And we're going to find out more about that. So how important it is for us to know about electrons. And you're going to find out we've learned quite a bit, but we have a lot more to learn. So we're going to talk about the principal quantum number. But before I get into this, I'm going to go into my notes because these are some of the things you need to know, as I took them from the book. But I thought I'd write them down because I thought, oh my goodness, we need to look at them not just in a paragraph, but look at them and put them together in notes. So let me go all the way up here. There we go. So first of all, we have quantum numbers, and they come in electron configuration. So what's an electron configuration? It is the complete arrangement of the electrons in an atom. It's how they're arranged, what we're talking about. Why is this important? Well, it's important because those electrons are what combines with other atoms' electrons to hold molecules together. And these molecules form new substances from which they came. And 2 elements form a molecule, and it'll be a total new thing, So in the midst of all this, the electron configuration is of utmost importance. So Schrodinger and his quantum numbers are very important because he said these are the characteristics of these electron shells and how electrons are configured around the atom. So the quantum numbers, there's 3 of them, or 4 of them, I'm sorry. And it starts with the energy level and onto the shape of the orbital and to the orientation in space and onto the spin. The energy level is labeled with an N. Just to remember that. N, probably a test question. N is the energy level. The L, kind of like the cursive L, is the shape of the orbital. The M is the orientation in space. And the MS, has a little S there for spin, is the spin. So we're going to talk about each one of these kind of, in some detail so that you can know what these quantum numbers really represent and some of the other ways to categorize them. And so let's go down here. Move down here. Here, there you go. So first of all, we have the principal quantum number n. That's this first quantum number. And it describes the electron shell. Now, there's some atoms have more than one shell. We know that. Some of them have many shells. So they labeled each shell would be N1 for the first shell that's there, that goes around the nucleus, N2 for the second one, and N3 for the third one. And to find out how many electrons on each one of these shells, they have devised a formula that works perfectly. And you just have to plug it in. And it's 10 N, that's basically this, N squared. So say they have one shell. We'll plug in one shell. One shell would be 1 squared would be 1 times 2 would be 2. So N would equal 2. So we put 2 in there. We have 2 shells. Put 2 in there. So 2 squared is 4 times 2 is 8. So 3 shells. 3 squared is 9 times 2 is 18. So it works perfectly with all the shells. This is a very important thing to remember when you're dealing with configurations of electrons, because you could know exactly what shell, and it will be on the periodic table. We'll learn that later. On to some of the values. As for the value, as the shell increases, like if you're on shell number 3 shells, the energy of the electron in that shell will increase. And also, the electron's probable distance would increase. And the number of electrons possible will increase. We know that by just plugging it in. And the size of the electron cloud would increase. So increases the size of the cloud, the number of electrons, the probable distance increases, and also the energy increases. Important that we know that the energy is going to increase of that because they have more electrons, right? More electrons, more energy, more distance, all of this in the size of the electron cloud. Now this all has to do, this whole principal quantum number, so N would be the principal quantum number. The energy shell would be that number. And so, so we'll go on from that point. Let's go on to the next. I'm going to move this down so you can see. Okay. Okay. So the number 2. Number 2 would be the shape of the orbital. We kind of talked about shapes before. So the shape of the orbital is of that subshell. Each shell is made of a subshell inside the shell. Can you believe that? And the second quantum letter, L, this is L, we're talking about the shape of the orbitals, and the letters for the shapes are in certain letters. So we need to know these letters. So what are these letters? Well, S means sphere. That's pretty easy. D, or P, actually, it's kind of weird because they have a P instead. P equals dumbbell. And D means orbitals. So you'll see, but you'll see the shells here as I go for the shells. Like in the first shell, S would have to be S. And the second shell would have to be S and P. And the third shell would be S, P, D. And the next shell would be S, P, D, F. And the last shell, S, P, D, F, G. You see that? And these are going to be different shapes, whether they're spheres or dumbbell lookings or clover leaves, and all these are going to be different shapes with the different numbers of shells. And so these are the shape. So let's talk about that a little more from your book. Let's go back to your book here. See here. So on to your book and the subshells. Let's go on to, we talked about the principal quantum number, and that's that number of N going on. And this tells about the energy of the electrons. All these things increase. Now the subshells were the letter L, but let's look at this table here. The table says the relationship of N and the possible number of shells that I just went over. And this says the possible number of shells for if there's, if the principal quantum number, that N number is 1, then that'd be C. And we went through all these things and different levels of this. So In each shell, there may be subshells having different shapes, as I said before. The number of possible subshells in a particular shell equals the principal quantum number. So this is how we go about it. So I kind of went over all of that. And here's some of the different shapes. Let's go in here. Basically, the effects of N on energy and the size of the electron cloud. So the bigger the electron cloud is, the more energy. You see, we have only two electrons here with the electron cloud, 2 electrons. So it's going to be small and less energy as you go 8 up to 18 on, and it'll get larger and larger, and that affects the energy level. And these are some of the shapes of the various orbitals. So here's an s orbital, here's a p orbital, d orbital on, and here's the direction of p orbital there. So the different shapes, that's what we're talking about here. And here we go to, hope you can see this here, is the different orientation of the orbitals there. And you can see this is how the dumbbell shape is the P, which is dumbbell, it would be P, X, P, Y. When you talk about the third quantum number, you talk about the orientation of the orbital to the axes of X, Y, Z, X, Y. You know when you have an X, Y axis, well, X, Y, Z would make it three-dimensional. So these are the pictures of how it would look. So you have, this is the X, be the X coordinate going this way. Whether you have X coordinate, this will be the, basically the Y coordinate going this way, because here you have, basically you have going this way. And then you'll have onto the Z coordinate, see how it can be presented. So this is just how it is presented in the midst of an orientation, and how is it going vertical or is it going horizontal or diagonal. And this is the combined of all of these combined P sublevels of PX, PY, P2, and they're all combined in this where. And this is the sum of all the orbitals in the shell. Pretty amazing. The pictures of these. So let's go down to the last. This part of the chapter is going to talk about the third orientation is the M. Remember, first we had the N was quantum number 1. The L was quantum number 2. And now we're going to have quantum number M. And so M is important. Why is that important? The M number is going to basically is going to be the number that describes, as it describes the orientation. It also is going to describe what it looks like even more by the orientation. And then we're going to go on to the spin. So let's go on. I'm going to go over my notes here a little bit here from this one too. Number 3 quantum number is called the magnetic quantum number 3. So let's go up. Okay. So magnetic quantum number 3 tells the orientation in space, which we kind of went over, that P being on 3-axis orbitals, D 5-axis orbitals, F 7-axis orbitals. And S has only 1-axis orbital. So you're talking about the 3, so you have 3px, you know that the 3 is going to be the number of shells, that would be the N number. The P, of course, is going to be the L number, which is quantum number 2, and the X is going to be the subscript there, and that subscript telling what kind of orbital, how its orbital subscript is. That's how they label it. So you might have to. So just remember, this first number is always N, second number is P, and on to X. It's pretty important. It's like your address. They're going to tell you, if you have your address, you're going to tell them what street you live on, what city you're in, and onto what state you're in. It's kind of like that. The N, the L, and onto the M number, number 3 number, which is going to be a subscript there of telling. And of course, the P has 3 axes, D orbitals, and it tells the orbital number there. So that's pretty important too. So each of those orbits, like I said, and that subscript is important. So we have to remember all of that. So let's go down further because I want to describe the spin. So the spin is the fourth quantum number, remember? As we had it before, as I said here before. First is the energy level shape, which is L. M is the orientation in space, and now we have the spin. So we're talking about number 4, spin, up and down. Basically, as they spin, they can spin, the electrons can spin, or I should say the photons, we're talking, can spin clockwise or counterclockwise. And they can spin in that fraction of space, as they call it, half spin. They label it by fractions, 1/2 positive or 1/2 negative. And they're always, the two opposites are usually paired in that way. Positive and a negative makes them basically neutral. There's also this Pauli exclusion principle. You need to know what that is. And basically, no two electrons in an atom may have the same set of 4 quantum numbers. So back to those quantum numbers. All the Pauli exclusion means is that no two different electrons have all of these the same. They're always going to be one different. Usually the spin's going to be different. So Pauli exception is that no two are going to have all 4 of those numbers the same. So let's go over that. No two electrons in an atom may have the set of 4 quantum numbers, the same set. So, okay, so now we're going to go over some of the electron configuration. So we went over here. Here's a picture here when I was talking about that subscript. This first letter is the N electron shell, and this basically being that P, and the subshell here being the X. The sum of all the orbitals in the shell is a spherical cloud. And so we can, at that point in that, put together, okay. So, and the spin number, we went through the spin number. Let's go over to this table here. So let me go down. Okay, table 7.2, relationships of N number and the type of orbitals. So we have, basically we have the N number and we have 1 s orbital. The sum of types of orbitals, 1. The maximum number, 2, because we've actually put that number 1 in that 2n square, and we get that. So on for 2, we have s orbital, and then I'll have three p orbitals, which equal 4 types of orbitals, 4 orbitals. But we'll also have a maximum number of 8 electrons. Number 3, 1 s orbital, 3 p orbit is 5, 1, 3, 5. It goes like 1, and then 3, then 5, and 7, kind of like odd numbers, huh? Onto the sum of the types of orbitals are 9, but also you plug it in the maximum of electrons and you get 18. So this kind of tells all about the quantum numbers, right? And here's a picture of the spin. So basically they spin, this one's spinning clockwise, it's a positive half. This is spinning counterclockwise, then it's a negative half spin. Those are the electron spins. Isn't it? You didn't know that electrons had different spins, did you? It's called the spin quantum number. And the spin quantum number is ms. So it has not only orientation, it has an S by its subscript there. That means spin, right? So let's go over this here. So see if we can see this well. Oh, sorry. There we go. Okay. So if we have a quantum number, the quantum number 1 is, this is just going over what we learned so far. We have the quantum number, which is number 1, which is the shell or the energy level. And it's an N, remember, and it indicates which electron shell or main energy contains the electron. And here's an example. See the picture of the shells within each other? N1, N2, N3. The second quantum number is the shape. And so here we have a subshell with these different kinds of shape. And it goes and indicates which subshell in a particular shell contains the electron. The different subshells have different shapes. So they're subshells. I mean, they're a shell within the shell, and they have shapes. So these are the main shells, but then you have a smaller subshell, and these are the subshells with the shapes. So you have this is L, this means subshell, and the shapes being S being sphere, P being this dumbbell, D being this looks like a clover leaf, and on to F, which is more, you can see, more complicated. So then we have number 3, which is the quantum number 3, and it has the magnetic quantum number M with M on it, and it describes the orientation in space. And we have whether it's on the x-axis or on the y-axis or on the z-axis. We find out which axis is on. And the last here at the bottom is the electron spin. It describes the spin clockwise or counterclockwise. It's measured in halves, so clockwise would be positive, and positive half, and counterclockwise would be, and it's always by an M with a little s subscript. Those are the things you need to know for the test. That's why I go over it so much. So now let's talk about electron configurations. So let me see. We're going to go to this one, but first of all, electron configurations. Let me see if I can go over this a little bit here in my notes. See if you can see this. Electron configurations are right here. So electron there's actually 5 rules that we have here, and we can go over those 5 rules of configuration. First of all, they have to have the same number of protons as electrons. So they can't have it. As for being neutral, it's going to have the same number of electrons as protons, unless they're going to turn into a negative or positive charge, ion. But anyway, the electrons are the lowest energy level orbital available. So electrons always go to the lowest energy, and they give off energy. They always want to go to the lowest energy available, like they're falling to the lowest point. And we have this word Abbau, which means building up. I think it's German for building up. And basically it's saying that they'll go to N number 1, they'll build up the first shell before they'll start in the second shell and the third shell. So they always build up. And that's a rule. That just means building up, as you can see. And then we have Hund's rule, and the electron will occupy, the single electron will occupy until it's paired. So single electrons will be dealt with. They'll deal with the single electrons before they pair. Pairing comes later. Just think of Hund's rule about pairing. Number 4, only 2 electrons can occupy one orbital, and especially that first orbital. I'm talking about 2 electrons. And the maximum number of electrons in each of these, and we kind of went over let me lift that up so you can see it better. I think I have it low as possible, so let's see. Maximum number here, S2, P6, D10, F14. Those are the maximum numbers as you plug them in with those kind of configurations. So, and then we're going to talk about, the electron configurations of the first 20 elements are here. So you have hydrogen here with S1, helium S2, and you can see the configurations getting greater and greater as they pair, as you go and have more electrons, all the way up to, calcium here. So you have all of these electrons and how they're paired, the electron configurations of those. So you can see 1s, then it goes, and as it gets bigger, you have the more complex P, and then it gets really complex, and you'll get others. But right now with all of these, mainly P and P3, P4, those are the orientations of the electron configuration. Okay, so let me go on to the Lewis symbols. Well, before I go into Lewis symbols, here's more about configuration, the relative energies in subshells. and with multi-electron atoms. So you start off, of course, with just one shell energy, and on as you go up, you'll see more energy, and how the subshells in each of these. In N2, you have two subshells. Here, this at 2p, 2s. These are subshells within. It's pretty complex, isn't it? Then you have another shell, number 3, and it will have 1, 2, 3 subshells here, and this is what they will look like: the S, P, and D. And then N4, you have, and it's overlapping here. You have 1, 2, 3, subshells here, and then the N5, you'll have this. So you're getting complicated on where the electrons are. It's complicated, but it's orderly, isn't it? So this table here is the electron distribution in atoms of the 4th period, but basically going on and saying how these electrons, you'll have N1s would be the subshell. It looks like a circle, like a sphere. Then 2 sphere, 2p, and then going on, and then you'll see. And then it'll say how many, they have in the midst of all that. So number of electrons. These are the number of electrons in each one of these. 2, 2, 6, 2, 6, 1. And you go on for that's potassium, that's calcium, and where the electrons are. You don't have to memorize that, I'm sure. Okay, this is what I wanted to get into, the last part here. And that is going to be the Lewis numbers. The Lewis numbers are going to look like, well, they're looking like this. This is a new way to put together with these Lewis numbers. The electrons in the outermost shell have valences, and these valences allow them to combine with other atoms, because the valence means that they can take in other electrons, and these electrons will hook up with other electron shells, and this is what brings chemicals reactions to make totally new substances. So when we look at this, the Lewis numbers, this is a Lewis number here, this symbol, okay? I hope you can see this. Let me see if I can go down further. There you go. Maybe down a little further, okay? So this is the Lewis symbol here. And then the Lewis symbol is this symbol. So these are all Lewis symbols. And then this is the atomic number, these little numbers up in the corner. The atomic number means how many protons, and there has to be about the same number. Well, there has to be, as for a neutral, it has to be the same number of electrons as protons. So the atomic number is the number of protons. And then these are your electron levels. So 2 would be the first shell, would be a 2. And then the next shell would have 8. And the next shell, there'd be 4 valence electrons. That means you have 4 electrons in that last shell. So this basically silicon, which can actually combine to fill up that shell. That valence means it can take in some more electrons, and that way they can hook together with combined in a chemical reaction. So if you look at the dots, okay, what are the dots? So the dots there are where those electrons in that last shell are to fill up to 8, the number 8. It always will fill up to the number 8. You'll have, an 8 would have full 2 here, 2 here, 2 here, and 2 here. So we only have 4. So this is how it comes together with 4. So the first electron's always here, that one. The second electron's here. The third electron's here. So 1, 2, 3, we have those. But then it skips up to here, over here, for the next electron, which it did there. But then from 4, it goes up to here, 5. And then at 5, it goes back down to here and fills this up, 7, 8. So it's kind of unusual, but I guess it wants to fill up the whole thing. So you go, first electron you have, 1, 2, 3, that's fine. And then it goes over here, it skips over here to 4, and then it skips over here to 5, and then it goes back to the skipped ones, which were 6, 7, and 8. So you'll do that because I think you're going to put together some of those. So it'll be kind of fun. So just to know what that Lewis symbol is, they made these symbols so they could tell how electrons can be involved in a reaction. And so that's pretty important. And these are all Lewis numbers on a periodic table here, so you can see. So if you took one, say that I would take, let's see, what should I take? Let's see, we'll take neon here. Neon is full. It has 2 and 8. That's the last valence is 8. So it has 1, 2, 3, 4, 5, 6, 7, 8 around. That's a Lewis number, and its atomic number is 10, so 8 plus 2 is 10. You see how these are organized? Like this one here says 2, 8, 18, 8. It goes 2, 2, 18, 18, 8. So it's like these numbers are put together in each one of these shells. But the last shell will have the red number, and that number will be the valence, where they can combine or can they not combine with that last valence. That's what valence means. Valence electrons are those that are involved in chemical reactions. So, okay. I'm going to go ahead and stop there, and then I'm going to go over this. This is kind of interesting. It's going to talk about lasers and how lasers, what are lasers, and how did they develop from quantum mechanics and light.